Structure and bonding. What is the difference? These are two words that tend to come up at the same time in a question, both at GCSE and at A-level, and so we can sometimes get away with not really knowing the difference. But bonding questions are going to get a lot more precise at A-level. You're going to need to be a lot more careful with your choice of words, just to make sure and to really understand the more in-depth stuff that you're going to do about intermolecular forces. So looking at an overview, there isn't anything more to this than what you've already seen at GCSE. So you should already know there are three types of bonding: metallic, ionic and covalent. And by doing that, we've looked at all the different types of combinations of elements that you can have. So metallic is obviously just metals on their own. Covalent would be just non-metals on their own, either pure elements like diatomic molecules, hydrogen, oxygen, H2O2, or ionic, which you've traditionally thought of as being metal and non-metal. Now, there are a small number of examples where metals can form covalent compounds. There are a small number of examples where ionic substances can arise from non-metals, but generally those rules are still going to apply to the majority of compounds and elements that you look at. And that's just to do with whether that element has a tendency to hold on to its electrons, which non-metals do, or whether that element has a tendency to let go of its electrons and have some other element take it, which metals do. And that's just to do with their position in the periodic table and the relative distance away that their electrons are compared to the charge inside the nucleus. You'll do a lot more about that when you look at how the energy required to remove electrons, things like that. But we've got metallic, ionic, covalent. There's only three types of bonding. Even more simple, hopefully, there's only two types of structure. Either everything is arranged in a giant lattice, or we're arranged as simple molecules. So let's visualize this and see if we can remember what the difference. Let's look at our definitions. Bonding, apologies for the bright yellow, I just really wanted to get the difference across, is the electrostatic attraction between charged particles, either between two different ions, or ions and electrons, or electrons and the nucleus. And we'll look at how the three different types of bonding relate to electrostatic attractions. Structure is just the way particles are arranged. Are they all arranged in a giant structure, or is there a small number of particles that are held together and then everything else is not bonded in that way? So looking at like how we could do diagrams and how we could explain the electrostatic attraction part. Well, in metallic bonding, the electrostatic attraction is between the metal ions because they've lost their outer shell electrons. Now at GCSE you may have got away with saying metal atoms when relating to metallic structure. Now we do need to be a bit more specific. They're not atoms because the whole point of the delocalized electrons is that they came from atoms which must now be ions. So notice in the diagram they've got plus charges on them because they are now positive ions in a sea of delocalized electrons. Diagram's not great because it's showing large gaps. There aren't really large gaps, but I guess it's to get this idea of electrons being able to move through. So there's an attraction there between charged particles. In the ionic, it's really easy to see where the attraction is because every cation is surrounded by anions and vice versa. So that's one thing to remember. The very way that ionic substances bond is how they become giant structures, because there's no reason for one chloride and one sodium ion to just stick together on their own. If there are any more sodium or chloride ions, they're obviously going to arrange themselves around the oppositely charged ions, and they're just going to keep doing that until we run out of sodium or chloride ions. Like when you're making sodium chloride in a little petri dish or an evaporating basin, you're waiting for the water to evaporate. You can get really big crystals, and that's just from however much sodium chloride there is going to make one giant structure. to the point where you can see it as a whole physical crystal or as a whole lump of metal. So that idea is that there's no foreseeable end to how many particles you can put into a giant structure. When we want to represent a giant structure in an equation, we just put the symbol for, or the formula for, like the simplest ratio of elements that there is. So in a metal, we're just going to simply write the symbol like Mg, which isn't really telling us that there are actually billions upon billions of magnesium ions in that lattice. Same with sodium chloride, we're just going to write it in terms of there's one sodium to every chloride. NaCl is completely different to HCl. Can't always see that in an equation. So just be wary of that you try and visualize what the different structures look like. Then we get to covalent substances. Lots of people, when it comes to the bonding, don't really think of covalent things as having charges, because we're very much not really thinking about, there's no ions present. But there must be some attraction, because they don't stick together just because they're sharing electrons or get a full outer shell. That's not really a physics explanation for why two atoms would stick together. So if you think of the two atoms coming together with their outer shells starting to overlap, what happens is that the electrons in those outer shells that end up between the two nuclei are going to be attracted to both of the nuclei. So that's where our attraction comes in with covalent bonding. It's the electrostatic attraction between shared electrons and a nucleus either side of it. That's really strong, and that means that if everything is held together with covalent bonds, like in a giant structure like diamond or graphite, then you'll have a high melting point. But most covalent substances, because you're sharing and it's very directional, means that there's an end to a covalent molecule. So once my hydrogen in methane has shared with my carbon, there is no other way for this hydrogen to interact with the hydrogen on another methane molecule. So although these bonds are very strong, these covalent bonds are very strong, there aren't really any strong bonds between this molecule and another. So this is where the big differences come about in melting point, boiling point, and other behaviour. Conductivity. You might be asked about conductivity. It's no more difficult than it was at GCSE. Does it have any charged particles? Yeah, everything does, protons and electrons. Can they move about independently of each other? Can the pluses move independently of the minuses, or can just one of them move? So, metals, delocalized electrons, they're always free to move, conducts as a solid, as a liquid. Ionic substances, ions can't move in that lattice, because if I move a chloride ion, it's going to get next to another chloride ion, so they're very fixed in place as a solid. If I heat it up enough to melt my ionic substance, then it will conduct, because the ions are free to move. If I dissolve it, same thing, and you would have done that in electrolysis. Covalent substances, graphite does, because 3 electrons are used in bonding for the carbon, 1 electron is delocalized. So graphite's the only non-metal with delocalized electrons. And then diamond, nope, all the electrons are used in bonding. Simple molecular substances, of course they do contain positive nuclei and they do contain negative electrons, but those electrons are always tied up in bonding, and those nuclei, can't obviously just move out of the atom. So there's not any ions or delocalized electrons that can move around, so there's no conductivity for covalent molecules under any circumstances. What about melting point? So how strong are the attractions holding particles together? So melting point is just to do really more with structure than with bonding. So all 3 types of bonding, metallic, ionic, covalent, they're all strong. So if you have a giant structure, it means that all of the particles in that structure are held together by either metallic, ionic or covalent bonding, depending on the type of structure. So all of those will have high melting and boiling points. Sometimes metallic bonds are stronger than ionic bonds. Sometimes ionic bonds are stronger than metallic bonds. That is just dependent on the charges on the metal ions or the ionic substances that are in the ionic compound. If you've got 2 plus 2 minus in an ionic compound, that will have a very high melting point. So generally, you just know that they've all got strong bonds. Covalent have the strongest, and that's why diamond is the highest melting point substance we know. Simple molecules, again, it's back to this idea that yes, covalent bonds are strong, but because it's not a lattice, then there is only weak intermolecular forces between two molecules, say of methane, or any of the molecules that you have. And so weak intermolecular forces don't require a lot of energy. That phrase doesn't really mean anything when you learn it at GCSE, intermolecular forces, but you're going to learn how they arise and the different types at A level, which will probably be a relief if you're the kind of person that wants to know how things work. They're still to do with charges, just very slightly different. Solubility is my next one, and I've realised that my head's in the way of this bit of this PowerPoint, but I'm going to soldier on. Can the particles form attractions to water molecules? If we're talking about can it dissolve in water, so sometimes ionic substances can. Solubility is something you're going to need to get into a lot more detail about at A level. Sometimes covalent substances can dissolve in water. I mean, water is a covalent substance. So when you learn more about intermolecular forces, you'll learn why some covalent substances do and some don't. When it comes to ionic substances, just learn that it's a clue. So if something has a high melting point, we're thinking, okay, it's some kind of lattice, one of the three. If the question then says it dissolves in water, it can only be an ionic lattice. So graphite and diamond can't dissolve in water. You would have to break covalent bonds. They don't dissolve, they don't break when you dissolve things. If you were trying to dissolve a metal, that doesn't really work, because if you try and pull the metal ion away, it will have to take its electron with it, and then you have a metal atom, and that's just not going to happen, like a metal atom on its own. So metals can react with water and lose that electron and form compounds. Covalent substances, nothing at all. They don't, like giant covalent. So if you see high melting point and dissolves, it's ionic. If you see high melting point, dissolves, solution conducts electricity, it's definitely ionic. Loads of clues. Malleability, not really going to do a lot about that at A level. You're not going to get asked much. Can the particles be pushed apart? Can you put a force on a lattice? We can only really apply this to a lattice because simple molecules, they don't have a sort of structure that you can mould because they're not one lump of solid usually. Metals can be shaped because as the layers of ions move, they take the electrons with them, so the attractions that are holding the structure together are still there. If I try and move a layer of an ionic lattice, a chloride ion is going to come right next to another chloride ion and a sodium ion and so on, and they are all going to repel each other. So the minute you try and put any movement at all into an ionic lattice, it will break apart and shatter, just like salt crystals do if you ever try to squash a piece of salt. When it comes to graphite, you've got an ability to the layers to slide past, but you can't mould a three-dimensional lump of graphite because of the strong covalent bonds, and you certainly can't mould diamond into shape. You can chip at it and break bits off, but you can't mould it. So that was just an overview to try and bring to the front of your mind different types of bonding, and realise that there's not probably as many as you thought. When you do intermolecular forces, you'll find out there's only 3 types of intermolecular force as well. So there's, it's probably a more grey area than you thought, but not as complicated as you might be worried about. Most of the time, you're just going to do comparison questions between 2 different substances that have different types of bonding. So between a metallic and an ionic. And the question would then be maybe comparing conductivity. Or you might have something about melting points, and it's usually a big difference in melting points, like ionic and simple molecular. So all you have to do for melting point is identify this is the strength, this is the type of bond that's present, ionic, covalent. This is the structure, giant, simple molecular. This is the force I need to break or overcome to melt it. Ionic bonds, weak intermolecular forces. Ionic bonds are strong, intermolecular forces are weak. So it's kind of learning a little script that will help you be a little bit more specific and not go too wrong. One thing that people always do is use the word molecular too much or use the word molecule. When you start learning about intermolecular forces, it's like your favourite word and you want to use it everywhere. But you can only use it in simple molecular things. So there's no such thing as a molecule if the substance is a lattice. So there are no molecular metals, no molecular ions, or there's no ionic molecules, and there's no molecules in diamond or graphite. So they are mutually exclusive terms. Make sure you can identify what sort of structure one substance has.